The Cobb-Douglas utility function we explored in graph 5.9 is of course a special case of the constant elasticity of substitution utility function, a special case where the elasticity of substitution is equal to 1 everywhere. We now explore the more general case of constant elasticity of substitution utility functions, and how differences in elasticities of substitution give rise to different types of indifference maps. The functional form of the constant elasticity of substitution utility function is written down here, where alpha can again take on values between 0 and 1. Alpha plays a role very similar to that it played in the Cobb-Douglas utility function that we explored in graph 5.9. We'll therefore set it to 0.5 here, treating both goods symmetrically. Rho, on the other hand, can take values between -1 and positive infinity, and in panel A we illustrate the indifference map that arises when rho is set equal to -0.8. In panel B we raise rho to -0.2, which begins to approach 0, which is the value that rho takes for the Cobb-Douglas utility function. The elasticity of substitution is given by 1 over 1 plus rho, which means we have a very high elasticity of substitution in panel A that decreases in panel B and then decreases even further in panel C when we set rho equal to 2. To be more precise, the elasticity of substitution begins at 5 in panel A, falls to 5/4 in panel B, and reaches only 1/3 in panel C. Thus, as the elasticity of substitution declines, the indifference curves move from those looking a lot like those for perfect substitutes towards those looking like indifference maps for perfect complements. Note again that in the graphs here we've set alpha equal to 0.5 and are therefore treating goods 1 and 2 symmetrically. As a result, the indifference maps that we've drawn are symmetric around the 45-degree line, just as they were in panel B of graph 5.9 when we set alpha equal to 0.5 in the Cobb-Douglas utility function. Were we to treat the two goods non-symmetrically by setting alpha at a value other than 0.5, the indifference maps would tilt away from that 45-degree line in much the same way as they did in graph 5.9. We can therefore translate directly our intuitions about the role of alpha in the Cobb-Douglas utility function to the role that alpha plays in the more general constant elasticity of substitution utility function here. And we now see the role that rho plays. As rho approaches -1, we get indifference maps that approach those of perfect substitutes. As rho approaches positive infinity, we get indifference maps that approach those for perfect complements. And as rho approaches 0, we get Cobb-Douglas indifference maps. You can explore this further by plugging in your own values for alpha and rho in one of the modules under the Exploring Relationships tab on this website.